Here's your script arranged without timing cues. The James Webb Space Telescope, JWST, is often hailed as the successor to the Hubble Space Telescope. Since its launch, the JWST has revolutionized our understanding of the universe, providing an unprecedented view of the cosmos, uncovering mysteries, and revealing sights never before seen by humanity. The JWST's cutting-edge technology has allowed scientists to peer into the farthest reaches of space, exploring galaxies, stars, and planetary systems formed billions of years ago. This essay delves into the many facets of the JWST, from its technological marvels to its groundbreaking discoveries, and discusses how it has reshaped our understanding of the universe. To appreciate the significance of the JWST, it is essential to understand its predecessor, the Hubble Space Telescope. Launched in 1990, Hubble provided astronomers with the first clear images of distant galaxies, nebulae, and stars, free from the blurring effects of Earth's atmosphere. Hubble's contributions to science are immeasurable, from helping determine the rate of the universe's expansion to observing the collision of comet Shoemaker-Levy 9 with Jupiter. Its deep-field images, capturing light from galaxies billions of light-years away, have given us a glimpse into the early universe. However, despite its successes, Hubble had limitations. Its primary mirror, with a 2.4-meter diameter, restricted its light-gathering ability, and its instruments were designed for ultraviolet, visible, and near-infrared parts of the spectrum. As astronomers pushed the boundaries of our knowledge, it became clear that a new telescope was needed, one capable of observing in the infrared spectrum, where it could peer through cosmic dust clouds and observe the universe's first galaxies. The idea for the James Webb Space Telescope began to take shape in the early 1990s, even before Hubble had reached its full potential. Named after James E. Webb, NASA's administrator during the Apollo era, the JWST was heralded as the next great observatory, a telescope that would look further back in time than Hubble, capturing the light from the first stars and galaxies that formed after the Big Bang. The JWST's design posed significant engineering challenges. Unlike Hubble, which orbits Earth at an altitude of about 570 kilometers, the JWST would be positioned at the second Lagrange point, L2, approximately 1.5 million kilometers from Earth. This location offers a stable environment with minimal interference from Earth's heat and light, but it also means that the telescope cannot be serviced or repaired by astronauts. To observe the faint, distant objects it was designed to study, the JWST needed a much larger mirror than Hubble. The solution was a segmented mirror made of 18 hexagonal beryllium sections coated with gold, giving the telescope a total diameter of 6.5 meters. This mirror had to be folded to fit inside the Ariane 5 rocket that would launch it and would only unfold once the telescope reached its destination. The JWST also required a sunshield to block heat and light from the Sun, Earth, and Moon, keeping the telescope's instruments at their operating temperature of just a few degrees above absolute zero. The sunshield, the size of a tennis court, is made of 5 layers of a special material called capton, which can withstand extreme temperatures. After years of planning, delays, and cost overruns, the JWST was finally launched on December 25, 2021. The launch was a momentous occasion, watched by scientists and space enthusiasts worldwide. The Ariane 5 rocket carried the telescope into space, and over the next 30 days, the JWST embarked on a complex and meticulously planned sequence of deployments. The telescope's sunshield was the first major component to deploy, a process that involved hundreds of mechanisms and thousands of parts working in perfect harmony. Any failure could have doomed the mission. After the sunshield was successfully deployed, the mirror segments began to unfold and align themselves. This process took several months, as each segment had to be positioned with nanometer precision. By mid-2022, the JWST had completed its deployment and alignment, and its instruments were ready to begin capturing data. The first images released to the public were nothing short of breathtaking. The telescope's ability to see in the infrared revealed the universe in a new light, with stunning clarity and detail. One of the primary goals of the JWST is to observe the first galaxies that formed after the Big Bang, over 13 billion years ago. These galaxies are so distant that their light has been stretched into the infrared spectrum due to the expansion of the universe, a phenomenon known as redshift. Hubble could only glimpse these ancient objects, but the JWST's infrared capabilities allow it to see them in unprecedented detail. In its first year of operation, the JWST made several groundbreaking discoveries. One of the most significant was the detection of galaxies that existed just a few 100 million years after the Big Bang. These galaxies appeared more massive and developed than previously thought possible, challenging existing theories of galaxy formation and evolution. Scientists had long believed that the first galaxies were small and slowly grew over time by merging with other galaxies. However, the JWST's observations suggest that some galaxies formed much more rapidly and became massive earlier than expected. This finding has prompted astronomers to rethink their models of how galaxies form and evolve. The JWST also captured images of cosmic structures that had never been seen before. For example, the telescope observed the intricate details of the cosmic web, a vast network of filaments that connect galaxies across the universe. These filaments are made of dark matter and gas and are the scaffolding upon which galaxies form and evolve. The JWST's observations of the cosmic web have provided new insights into the large-scale structure of the universe and the role of dark matter in shaping it. The JWST has also revolutionized our understanding of star formation and stellar evolution. Stars form in dense clouds of gas and dust, which block visible light. However, infrared light can penetrate these clouds, allowing the JWST to observe the process of star formation in unprecedented detail. One of the telescope's first targets was the Orion Nebula, a stellar nursery located about 1,344 light-years from Earth. The JWST's images revealed hundreds of young stars, some of which were still embedded in their natal clouds. These observations have provided new insights into how stars form and evolve, as well as the processes that lead to the formation of planetary systems. The JWST has also observed the final stages of stellar evolution, capturing stunning images of dying stars and the nebulae they create. These observations have shed light on the processes that govern the end of a star's life, including the formation of white dwarfs, neutron stars, and black holes. One of the most exciting aspects of the JWST mission is its ability to study exoplanets, planets that orbit stars outside our solar system. The telescope's instruments are capable of analyzing the atmospheres of these distant worlds, searching for signs of habitability and potentially life. In its first year of operation, the JWST made several significant discoveries related to exoplanets. One of the most notable was the detection of LHS 475b, an exoplanet located about 41 light-years from Earth. The JWST has also observed other exoplanets with diverse atmospheres. Some of these planets have thick, hazy atmospheres rich in methane and other hydrocarbons, while others have clear atmospheres dominated by hydrogen and helium. These observations have provided valuable data on the diversity of planetary systems and the conditions that might support life. One of the most intriguing questions in astronomy is whether life exists elsewhere in the universe. While the JWST cannot directly detect life, it can search for biosignatures, chemical markers that might indicate the presence of life. For example, the detection of oxygen or methane in an exoplanet's atmosphere could suggest the presence of biological processes. The JWST's ability to study exoplanets has opened a new era in the search for life beyond Earth. As the telescope continues to observe more planets, it will provide crucial data that could help answer the age-old question: are we alone in the universe? In addition to its studies of distant galaxies and exoplanets, the JWST has captured images of some of the most beautiful and mysterious objects in the universe. One of the most striking is the cosmic tarantula, a massive star-forming region located in the Large Magellanic Cloud, a satellite galaxy of the Milky Way. The cosmic tarantula, also known as 30 Doradus, is a vast region of gas and dust where thousands of new stars are being born. The JWST's images of this region reveal intricate filaments of gas, glowing clusters of young stars, and the remnants of supernova explosions. These observations have provided new insights into the processes that drive star formation and the life cycles of massive stars. The JWST has also captured stunning images of nebulae, such as the Carina Nebula and the Eagle Nebula, revealing details that were previously hidden from view. These images have not only captivated the public's imagination, but have also provided valuable data for astronomers studying the birth and death of stars. While the JWST has made incredible strides in our understanding of the universe, its journey has not been without challenges and controversies. The telescope's development was plagued by delays and cost overruns, with a final price tag reaching nearly $10 billion, significantly higher than the original estimate. These issues led to debates within the scientific community and among policymakers about the project's feasibility and value. Some critics argued that the resources devoted to the JWST could have been better spent on other scientific endeavors, while others contended that the telescope's potential for groundbreaking discoveries justified the investment. Despite these challenges, the JWST's success has vindicated the decision to pursue the project. The telescope has already exceeded expectations in its ability to observe the universe in unprecedented detail, and it is expected to continue making discoveries for years to come. The JWST's success has also highlighted the importance of international collaboration in space exploration. The telescope is a joint project of NASA, the European Space Agency (ESA), and the Canadian Space Agency (CSA), with contributions from scientists and engineers worldwide. This collaboration has not only made the JWST possible, but has also set a precedent for future space missions. As the telescope continues to explore the cosmos, it will undoubtedly inspire future generations of scientists, engineers, and explorers to push the boundaries of our knowledge and seek answers to the most profound questions about the universe. The James Webb Space Telescope has revolutionized our understanding of the universe, providing an unprecedented view of the cosmos and uncovering mysteries that have long eluded astronomers. From observing the first galaxies that formed after the Big Bang to studying the atmospheres of distant exoplanets, the JWST has made discoveries that challenge our current understanding of the universe and open new avenues for exploration. Its success is a testament to the ingenuity and perseverance of the scientists and engineers who made it possible, as well as to the power of international collaboration. As the JWST continues its mission, it will undoubtedly reshape our understanding of the cosmos and inspire future generations to explore the mysteries of the universe.